Thank you very much for the introduction and welcome to this talk. This is a project that happened in collaboration between ETH Zurich and TU Delft, and it's called GravoTet, a fast multi-grid hierarchy construction for tetrahedral meshes. Let's get right started. So we walk around Istanbul and we meet this octocat. And the first thing that comes to my mind is, can I tetrahedralize this and then solve a heat equation on it? So this cat is now not just a surface, it is a volume full of little tetrahedra. And typically when you try to solve something like this, a PDE with a Laplacian on a volumetric mesh, you would instinctively first try a direct solver, but direct solvers scale poorly. And when you have volumes, you get a lot of vertices on the inside. So the scaling becomes quickly very expensive. And the state of the art that often a lot of people use is called Holmot, for example, a sparse optimized solver. But even that will struggle poorly when the resolution goes into the million. And the first question we have is like, oh, is there a way to do this faster? And there has been for a while. These methods are often called multigrid methods, and they operate by working on different resolutions. So you have a sparse symmetric matrix system, and it's just AX equals B, and A is a sparse symmetric matrix, and you leverage the computation, like different methods for different resolutions. So you can focus your computation on the high resolution details using something like Gauss-Seidel iterations, which converges poorly globally, but converges well when you just try to reduce the high frequency error. So you go to the high resolution to reduce the high frequency error using Gauss-Seidel, and then you go to the medium resolution, and then you can focus on those frequencies to resolve. And then you can continue this until you go to a very low res, and there the scaling problem that you had at the beginning with the too high resolution to use a direct solver doesn't happen anymore, and there you can use a direct solver. And generally in multigrid methods, you then want to communicate between these different resolutions. And the basic algorithm is called the V-cycle algorithm because you travel down and up and then down and up and down and up again, this hierarchy, and you pass on the residual, which is called residual. It's basically the error. You pass it down, you solve it, then you pass it up again. And the main ingredient for a multigrid method is the so-called prolongation matrix. The prolongation matrix tells you how to map the values of one level to the next level. And also the transpose of the prolongation matrix tells you how to map the higher level to the lower level again. So it's basically interpolation, extrapolation. And it's a series of matrix, one matrix for each level transition. And if you take the original matrix system, you can just slap on the left and on the right a prolongation matrix. And then you're reducing your big matrix to a smaller space. And then you can continue working on that. And you do this for every level. So the key ingredient is prolongation matrices, and they are not unique. You can have many different multigrid methods giving you different prolongation matrices. And some of them can be like designed to just have very few levels. You can have a lot of levels of hierarchy. You can have different weights on how you represent the higher level on the lower interpolations. And there's a lot of freedom to do. But generally, there is also a lot of difference how fast these algorithm converges based on how good your choices of these prolongation matrices are. And this is what we want to do. We want to find good prolongation matrices. So we have a 3D volume that we want to use multigrid on. And there are different approaches to deal with 3D multigrid. Very basic, popular, and awesome are grid-based methods, but they are not suitable for representing the curved surfaces when you are reducing the resolution. So on your high-res resolution, you can use a lot of cubes to represent your curved surface, but then you go lower, 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 and at the bottom, you still want a good representation. And this is not going to fit well with cubes. Next are graph-based methods. So they use the connectivity of the mesh, and they're already much better, and also our closest related work is going to be a graph-based method that we're going to work with. But generally, they will, as we will show, converge slower. And then there's a third class that is directly designed for tetrahedral meshes. The problem is that they work mostly on edge collapsing and then repairing the broken tetrahedra that you get once you collapse. And we do not compare against them because they take hours for the meshes we are trying to use, while we are trying to build the prolongation and solve it within seconds. So what we want is fast construction of prolongation matrices and good convergence. And yes, we can actually do that by introducing our new method, GravoTet. GravoTet means Graph-Voronoi Tetrahedral Multigrid method. And it's a fast and effective coarsening strategy. That is the idea behind it. And it starts by having a prioritized sampling of what vertices do we take into the next coarse level. After that, we focus on the surface, because the surface is where we have more details, where the boundary condition is supposed to survive. So we give the surface extra attention. We do a approximately Delaunay connectivity on the surface. I'll explain that soon. And then we continue to the interior. Once the surface is established, we can then connect the interior of the our subsampling, our hierarchy. And after we have done that, we have like a set of tetrahedra, and then we can compute the barycentric weights to actually get the prolongation matrices. So let's go into some details. The prioritized fast disk sampling, we do it by first computing a feature on every vertex. So for example, a corner of the cube will have a strong variation of its normal around it, and then we give it a higher value because of that, and then we will sample it first. This will be a prioritized vertex. We call it like, oh, this is an important vertex, so we should make sure it doesn't get lost during the sampling. So edges of a cube would survive, or tips of the ear would survive this way. And then we sort all the surface vertices by these features in order for the fast disk sampling to then start with the important vertices. And the basic method of the fast disk sampling is take a vertex, build a radius, and instead of querying for the nearest points, we simply look at the neighbors in a 2-ring at max. And then if a vertex is too close, we say, no, remove you, go away, shoo shoo. These red marked crossed out vertices will not be part of the next coarse level. And then we continue this, we take the next vertex, we look at the radius, we start removing more vertices. And this is very fast, linear time. And speed is something that we really need in order for our goal to be reached, to have fast results. So we end up with 5, in this example, 5 coarse vertices that go into the next mesh generation. And an added bonus, because we sorted the important vertices first, and then we sampled them first, the next coarse resolution already has the same ordering preserved. So the important vertices stay in the front for the next generation after. And now to the core idea. We have heard this now plenty of times. Voronoi diagrams dual create Delaunay connectivity. Delaunay connectivity is our favorite type of connectivity. It makes very nice meshes. But getting actual Voronoi diagram Euclideanly takes some more effort. And we avoid that effort by going for a graph Voronoi diagram that we can quickly compute using the connectivity we just had. And then we just take the dual of that and assume that this is good enough. It's not going to be perfectly Delaunay, but we will see that the properties it has in its barycentric weights are good enough. I mean, actually very efficient for multigrid method. So how do we do this? The clustering part now. So we have these orange vertices. We want to connect them with each other. And a straightforward way to do this is to look at the fine vertices, so the green ones, and look at where are they connecting. If every green vertex has a closest coarse orange vertex, and if 2 green vertices are connected that belong to different coarse vertices, we connect the coarse vertices. So it's something you can do fast with Dijkstra's algorithm and starting multiple locations at once. You can quickly scan which vertices belong to which coarse mesh and coarse vertex, and then connect them with each other, and then you get something like this. Also very fast. And we start by only doing this for the surface vertices. So we had sampled all the vertices with prioritization for the surface, and then we connect the surface vertices, and then only after that we go into the volume. And the reason why we're doing this is if you don't, then you end up with this type of mesh, and it should make you feel weird in your stomach when you see it, because the surface is all blah, 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 because it wasn't taken care of, prioritized. And this is why I'm doing the other way. We get this nice surface, and we need the nice surface on the coarse resolution because our boundary value problem is defined on the surface. And if the surface at the bottom is all mushy, then we cannot expect good convergence of our solution. Once we have that, so imagine you had all this in 2D. Now we can go into 3D. So the surface will now grow into the interior of the volume. And with the exact same connectivity rules, we just continue, and then we have all the vertices connected. And then we want to compute the prolongation matrix weights. So what we do then is we look at the coarse vertex connectivity. We look at every fine vertex, for example, this green one, and then we ask, in which tetrahedra are you inside of? And that's a quick test of looking at the neighboring vertices, finding the coarse vertices and checking, are you inside of it? And then you take the barycenter coordinates of the green point relative to the tetrahedra that it's inside of. And those will be your prolongation weights. So those are the parameters of interpolation that you then use in your multigrid steps. And notice, though, that because we used a graph Voronoi, we're not actually getting exact tetrahedra. Many of them will be fine tetrahedra, but they may overlap, and they may even collapse. And it is actually okay. Don't be afraid of collapsing tetrahedra when you're doing only barycentric computations. You're not computing the inverse mass matrix, because that would explode, but you're just having a tetrahedra that might collapse into a triangle, but the barycentric interpolation is still reasonable in that. So, and then this is a repeated. So we do this once to get to a lower resolution, and then we can do it again to get an even lower resolution. And generally, we stop once we are below 10,000 vertices. And the tetrahedra that come out are all reasonably shaped. They are nicely spaced away from each other because the vertices were selected using fast disk sampling to be in a nice distance from each other. And then we can run our algorithms on this. So for example, 500,000 vertices in the input, and then we can compare our method together with, wait, this is the green one. This is a graph-based method, and these are, the other two ones are algebraic multigrid methods. The algebraic multigrid methods only care about the matrix. The graph-based method, oh, sorry. Okay, I shouldn't use this. The graph-based method uses the connectivity of the mesh, and then our method uses the barycentric weights. And we see from the total computation time that the actual build time of ours is bigger. It takes more time to build up, but the solving time, it's much faster. And this is sort of the benefit of having better prolongation matrices, putting more attention into building them. And then the direct solver at this resolution is still competitive for Poisson problems. Then we can look at biharmonic problems, which are inherently more ill-conditioned. And there we can see that our method's added convergence quality is really beneficial for this, while the other methods really struggle to get anywhere close to the tolerance. And the direct solver still holds up for this resolution, but we can now up the resolution, like, oof, give me more, give me more. And we end up, for example, with 2.8 million vertices as the input TET mesh. And then our method still continues to do well for the Poisson problem, while the direct solver fails because it's very memory intensive and scales poorly. It already starts to fail on my machine at 800,000 vertices. And then the graph-based method is still doing fine, but then let's look at the biharmonic problem. And there the competition stops. Most methods really converge poorly or would take almost forever, while the direct solver also has no chance for this resolution, and our method still holds up. And as you can see, most of the computation time now goes into the solving itself. The buildup is now minimal. Yeah. We have tested this on plenty of meshes for performance. And in generally, after 100,000, 200,000 vertices, our method starts to beat, not just in build time, but in total time. So this is important because a lot of multigrid methods are designed to solve faster, but the build time is sort of considered to be separate because they think of, oh, I want to run a thermal simulation, so I only need to build once and then I solve all the time. What I'm presenting here is something that where the build time with the solver time is actually together very nice. And for the biharmonic problem, the competition ends earlier. Many methods time out, or the Hornung² has problems. Direct solvers fails at already 800,000 vertices. And yeah, that would be my presentation. I have more slides, but I had some time pressure. And you can ask me about mesh quality and ablation study and sparsity if you want to. Thank you very much.